Right, so a very good evening to you guys. Now before I start with the topic, I would just take 1 minute of your time to help you understand something that I have newly started, and that is my YouTube channel, The Chain Reaction, which will in which I will be making videos which will be purely in Hindi. Okay, so many of you have requested me to make videos in Hindi, and it would be unfair to the people who watch my videos who are familiar with English and are unfamiliar with or are not familiar with Hindi. So I thought it's better that I separate both the channels. So one channel will be for Hindi, where I will be taking videos purely in Hindi language, and then this particular channel will have videos in English only, right? So for those of you who are uncomfortable with English, or who find it difficult sometimes to understand videos in English, they can go ahead and follow my channel, The Chain Reaction, right? So please go ahead and subscribe that channel. I will start to upload videos on that particular channel really soon. And so the reason why I have thought of making this particular video about thermodynamic and kinetic control is because I generally post one question each and every day on this platform, which is called Reagent Blues, right? So there's a Facebook group called Reagent Blues, and there's a Facebook page also called Reagent Blues that I manage, and then there's an Instagram handle as well. So if you like, you can go ahead and follow this Reagent Blues on Instagram and Facebook. And so on the Facebook, I generally post one question each and every day, and many of you answer those questions. But somehow I recently posted one question which was related to this topic, which is kinetic and thermodynamic control, and many of you answer all those questions, but that particular question nobody answered, right? So I thought maybe there is some problem with the concept, and thermodynamic and kinetic control is actually a very important concept, right? So we are going to discuss that. And anyway, if you if you would like to solve certain questions that I post daily, I would request you to go ahead and follow this page, Reagent Blues. And on Instagram I post molecule of the day, or some interesting molecules, or some interesting molecules or ideas where you can do research on, right? So if you are interested in that, you can go ahead and follow my Instagram handle and my Facebook page and group as well, right? And for those of you who are comfortable in Hindi, go ahead, The Chain Reaction, that's the name of the YouTube channel. I'll post a link down below, so in case you're not able to find it because it's a new channel, so you can just click on that link and subscribe to the channel, right? Now let us begin with this topic, right? Okay, so thermodynamic and kinetic control. Now what do you understand by thermodynamics? So thermodynamics is basically concerned with the stability. If I talk about organic reactions, when I say thermodynamic control, it basically means that I'm talking about your stability. And when I talk about kinetic control, I am talking about the rate of the reaction. Okay, so when I'm talking about the kinetic control, I'm talking about the rate of the reaction, and when I'm talking about the thermodynamic control, I'm talking about the stability. So how do we decide which is more stable and which is more faster, right? Now there's a misconception among the students, and I'll clear that misconception first. They think that something which is more stable, okay, so if we are going from reactant A to reactant B, then there's also chance of from A we can get C. Okay, so from A we can get C, and from A we can also get B. Now what do students think is that whichever is more stable, okay, whichever of the two products, B and C, is more stable, that will be the major product. Okay, but that is not always the case, because it also depends on the transition state. So this is where I am going to help you understand this particular concept, that even if the product is more stable than say some other product which can also be formed, it does not make that particular product the major product. It depends on the conditions, and that is what kinetic control and thermodynamic control is all about, right? So let us now discuss the concept. Okay, so let's say I'll draw the diagram, the energy for the products. Let's say we are having a reaction like I explained to you. From reactant A we can get reactant B also, and from reactant A we can also get product C also. So we can get two products, either product B, or we can also get product C from A, right? Now if I plot the reaction coordinates, so let's say this is a reactant A which is over here with some energy. Okay, now what I am doing is okay, so now it progresses and it comes down, and this is your product B. Okay, and I'll take a different marker to explain this concept in a better fashion. And let's say we have another diagram like this, and this is your product C. Okay, so I hope it is clearly visible to you. This is your reactant A, this is your product C, and this is your product B. This is the transition state energy. So on the y-axis we are measuring the energy. Okay, on the y-axis we are measuring the energy, right? Okay, so A is of higher energy, and you can clearly see that B and C are of lower energy. So B is somewhere even lower. So the more lower the energy of the product, the more stable the product is. So we can see clearly that B is of the lowest energy. So B is the most stable product, right? So B is the most stable product. Whereas if you see C is lower in energy than A, but it is obviously higher than B. Okay. Now B is the most stable, so B is our most stable, right? So B is most stable product. So you might be thinking, or many students might be thinking, that B will be the major product, but that is not the case. Why? Because if you see the transition state energy, so this is your transition state energy. So before the A can get converted to B, it has to reach this energy which is called the transition state energy. So there is a transition state which is formed whenever a reaction is progressing, right? There is a transition state formed, and once that transition state energy is reached, only then the product B can be formed. Now if we do not provide that kind of energy to this reactant A to reach this energy, if we only provide some energy so that the reactant A can reach this particular point, which is the transition state energy. So this is the transition state energy for product C. So even though product C is less stable than B is more stable because it is of lower energy, right? So even though C is of higher energy than B, yet the transition state of C can be lower. It does not mean that the transition state of C should also be higher. Okay, just because C is the product that is formed is of higher energy does not mean that the transition state also has to be of higher energy. Okay, so it is independent of what the transition state energy is, right? So the energy of your product and the energy of the transition state that is required to generate that product, they both are totally independent of each other. Now if you see over here, the transition state energy of C is lower than transition state energy of your B. So this is the transition state energy of B, which is lower. Now what we can understand from this is that if I provide some energy, if I provide some minute amount of energy to this reactant A, so that it can only go up to the transition state energy of C, I will not provide it that much energy that it can reach to this point, the transition state energy of B. I will only provide it the energy required so that it gets to this transition state, that is C. So then in that case the major product formed will be pure C. So a compound C, even though less stable, will be formed in major quantity, right? So this is what I mean by kinetic control, that even though your C is less stable, it is of higher energy than A, yet it is formed as a major product. Why? Because I have only supplied it with that much energy so that it can reach up to the transition state energy of C, and it cannot go up to the transition state energy of B. And to form product B, which is more stable, it has to reach the transition state energy that is required for the product B, right? Now how can I do that? If I take lower temperatures, okay, if I take lower temperatures, then at low temperatures, obviously the energy supplied will be less, and if the energy supplied will be less, so maybe the transition state energy of B cannot be reached at lower temperatures. Whereas if I take the reaction at high temperatures, if I take the reaction at high temperatures, this reactant A will be supplied with enough energy that it can reach to the transition state of B. Okay, so if it reaches to the transition state of B, then obviously your B will be the major product. So from this we can conclude that for low temperatures we always look for kinetic product, and for high temperatures we always go for the thermodynamic product. Okay, so from this we can conclude that for thermodynamic control, okay, so from this what we can conclude that for your thermodynamic control we require high temperatures, and for your kinetic control we require lower temperatures. Also the reaction should also be short. Okay, by short means, let's say if I am doing a reaction, let's say at room temperature, which is in between your thermodynamic and kinetic. So if I do a reaction for, let's say, just 5-10 minutes, then obviously your kinetic product will be dominant. And if I do the same reaction for a very long period of time, for let's say 10 hours, 20 hours, 24 hours, then obviously your thermodynamic product is formed. Okay, because you are supplying around somewhere around 25 degrees Celsius, which is not even high and not low also. So in those cases it depends on your it depends on the reaction time. So for how long or for how long time span of time you are doing that particular reaction, right? Now let's take an example so that you can understand this concept in a better fashion, right? So let's take the example of 1,3-butadiene. Okay, so we are going to take this very simple example. This you will find it in any standard textbook. And let's say we add H plus to it. So what will be the transition state that will be generated? The transition state that will be generated will look like this. So your alkene will attack this H plus, and the transition state that will be generated will be, so we will get a carbocation over here, right, like this. So this is one transition state that is generated. I'll show it in square brackets. The other transition state that is generated is either this can be formed, or this double bond can show resonance, and it can migrate like this, and the carbocation now will be generated at this particular place like this. So this is so basically what is happening is this bond is migrating like this, so the carbocation is generating at the terminal site. So these are the two transition states that can be generated. Now if you look at the transition states, which transition state is more stable? Obviously this transition state is more stable. Why? Because this is a secondary carbocation with resonance, whereas the one formed over here is a primary carbocation with resonance, and obviously a secondary carbocation will be more stable. So this transition state is more stable. Now if I bring a nucleophile, let's say chloride anion, if I bring a nucleophile, let's say Cl minus, so what will the Cl minus do in both the cases? In this case the Cl minus will go and attack this center and in this particular case the Cl minus will go and attack the terminal center. Now remember the transition state for this is more stable. Okay, so the transition state, I'll just I don't have a different colored marker, I mean it's not working, so I'll buy one soon. So this is more stable, this transition state is more stable. Okay, so the product formed in this particular case now will be, I hope you are able to see that. Yeah, so this is your product formed, and in this particular case the product form will be this, right? So these are the two products formed. Now if we look at these two products, which one is more stable? Can you tell me which one is more stable? Obviously this one is more stable, and what is the reason for that? Well, in this one, if you see the alkene is mono-substituted alkene. What do I mean by mono-substituted? Basically, there's only one methyl group attached to this particular, like one CH group attached to this particular carbon, to this alkene, because over here we have two hydrogens, so there's no substitution over here, but over here we have one carbon attached, so this is mono-substituted alkene. Whereas if I talk about this particular case, this is a di-substituted alkene, because we have a carbon attached on this side as well, and there's a carbon methyl group attached on this side as well. So this is a di-substituted alkene, and this is more stable. This is more stable. So now what do you see is the transition state for this was more stable. For this particular product, the transition state was more stable, but the product itself is not as stable as when compared to this one. And in this one the transition state is less stable, and the product is more stable. So now the transition state, the reaction coordinate diagram will look something like this, the one that I had drawn earlier, where, so I'll draw it over here, okay, right. So now if I draw the reaction coordinate diagram, so the transition state for your, so we have some product A, let's say this is for 1,3-butadiene, and we will draw the transition state which is more stable, and it will give us this product. Let's say this product is our product B. This is our product B, so this will give product B over here. And the transition state is, energy is lower because it was a secondary carbocation with resonance, which will be more stable. Whereas for your product, let's say this product is C, let's say this product is C, so for C, what is happening is, there is a higher transition state energy. Why? Because it was a single, the transition state was a single, primary carbocation, sorry, it was a primary carbocation with resonance, because of which the energy of the transition state for your product C will be higher, okay, but it is more stable in energy, like it is as compared to your product B, it is stable because it is of lower energy, right? So now you can see this is the diagram that we have drawn. Now if I take lower temperatures, then the energy, I will not provide enough energy for this product A to reach up to the transition state of C, and that is why the major product will be B, because this reactant A is not being provided with enough energy at very low temperatures, then it can reach up to the transition state that is required to get converted to product C. So then B will be the major product. But on the other hand, if I provide high temperatures, then in that particular case, what is going to happen is, I am providing enough energy for this reactant A to go up to the transition state to form product C, and since product C is more stable, then in that particular case this will be the major product. So that is why at high temperatures this is your major product, and at low temperatures this will be the major product. And this is a very important concept, because in the examinations what happens is, examiners do this thing to test your concept. They will provide you energy, either they will give you, let's say, -20°C, or they'll just give you a triangle, or they'll just write, let's say, heat. So if they are writing heat and you see an alkene, you have to make the thermodynamic product, the one which will be thermodynamically more stable. And in case you have been given low temperatures, let's say around -20, -30°C, then obviously you will have to make a product which is kinetically favored, right? So this is how you accumulate all the information and then come out with the answer, right? So obviously the examinations will never be easy. These kind of questions in fact are asked in your IIT JEE as well, not just your NET and GATE or your IIT JAM. And in fact, I will request you guys that if you actually need to do well in your IIT JAM paper or in your GATE paper, okay, definitely practice questions from your IIT JEE mains and advanced, because the physical chemistry questions in those particular in that particular examination is of very high level, right? Some of the questions from GATE or some of the questions from even NET, if you talk about the physical chemistry part, are actually asked from your IIT JEE, right? Or it could be vice versa, I don't know, like which paper came first. But obviously the GATE exam is made by IITs, the JAM exam is made by IITs, and the IIT JEE paper is also made by the same professors from the same IITs, right? So definitely there will be a repetition of questions in all these three examinations, right? Now let's take one more example to clear a concept even further, right? So that no confusion is left regarding this particular topic, right? In fact, there are two more examples. There's one cyclization example as well, which is actually very important for higher level examinations, right? Okay, so let's take one more example. This was the question that I had asked in my Reagent Blues Facebook page, right? This was the question that was asked. So I'm adding a base to this. Let's say I'm adding a NaOH, and I asked what will be the major product in this particular case. So we see that there are two acidic hydrogens, one is this OH and one is this OH. So this OH minus can abstract either this hydrogen or it can abstract this hydrogen, and will lead to the formation of O minus, right? And similarly it can lead to the formation of O minus even here as well, right? So if it leads to the formation of O minus in this particular case, this O minus is then going to attack this carbon over here, and this bromine will leave. Okay, so it will attack this carbon over here and bromine will leave, and the attack of this O minus will be from above the plane, because this bromine is present below the plane. So the attack of this O minus, it will be like a SN2 reaction, right? It will attack from the opposite plane, and the product that will be formed will be basically a three-membered ring. Sorry, I got confused. Okay, just a second. So just sorry for this interruption. 1 2 3. So 1 2 3 4, fourth center. 1 2 3 4, right? So this is our fourth center, and to this we have our oxygen attached. Sorry for this interruption. Right, so this is going to be the product with this O above the plane. Right, I'll just count the number of carbons and oxygens. 1 2 3 4 5 6. So 1 2 3 4 5 6. Yeah, so this is the product that is going to be generated, right? So sorry for the interruption, I got confused. Anyway, so this will be the product. And what if this O minus is abstracted? Instead of this one being abstracted, what if this O minus is abstracted? So if this O minus is abstracted, what will be the product? The product will be basically, we'll have OH in this case, 1 2, right? And then we'll have a four-membered ring. Right? 1 2 3 1 2 3 4 5 6. So this will be the product, and over here we'll have this above the plane. Right, so this will be the major product. In this particular case, this will be a three-membered ring, and in this case we'll get a four-membered ring, right? So which will be kinetically favored and which will be thermodynamically favored? Okay, so in this case actually there's no thermodynamics and kinetics involved, because generally if we do this reaction at very low temperatures, if we do this particular reaction at low temperatures, your three-membered ring is formed. So three-membered ring is also strained, and your four-membered ring is also strained. Okay, both your three-membered rings and your four-membered rings are your three-membered and your four-membered rings are strained. But if you see this O minus, the proximity to this particular carbon, the proximity of this O minus to this particular carbon is it's quite closed. Okay, if you imagine, if I have four-membered ring on my right arm, and if I have a three-membered ring on my left arm, obviously it will be easier for me to grab that three-membered ring because it is closer to me. It will be difficult for me to go stretch my hand and grab the four-membered ring, right? Similarly, this O minus can easily come into an orientation so that it can attack this particular carbon, whereas this O minus, which is a little further away from the your electrophilic center, from where it is going to attack, because it is further away, so it will be difficult for it to come into a proper orientation so that it can attack this particular carbon, because of which what is going to happen is that your three-membered ring is generally kinetically favored. Okay, thermodynamically it's not favored because it is of very high, it is of very high energy. It's extremely strained. A three-membered ring is extremely strained, because of which it will not be thermodynamically favored. but kinetically it will be favored. Whereas a 4-membered ring, it will not be thermodynamically favored, and nor will it be kinetically favored, because again 4-membered ring is also strained. Okay, a 4-membered ring is also strained, so it will not be thermodynamically favored, nor will it be kinetically favored. So even if this reaction was carried out at, let's say, very low temperatures or very high temperatures, yet this will be our major product. But what I'll do now is, instead of this 4-membered ring, what I am going to do is I am going to attach one more carbon. Okay, now what I am going to do is attach one more carbon. Okay, so now if the attack takes place, so 1 2 3 4 5, now if the attack takes place, we'll have a 5-membered ring, and a 5-membered ring is thermodynamically very stable. Okay, a 5-membered ring is thermodynamically very stable. Okay, so if I draw the product, now we'll have a 5-membered ring like this. So now if I do this was the question that I had asked in the page, which the students were not able to answer, or they did not see that particular question. Now if I do this reaction at high temperatures, let's say of 200 degrees Celsius, this is our major product. But if I do the same reaction at, let's say, minus 50 degrees Celsius, the 3-membered ring will be the major product. Why? Because this one is thermodynamically more stable, this is kinetically more stable. Here you cannot explain, I think, by the transition state. Here you cannot explain this concept, this thermodynamic and kinetic control by transition state. Here you have to use the principle of proximity or logic, because this O- has to attack this carbon, and it has to be in the correct orientation, because it has to attack from the opposite plane. So obviously if you have a shorter chain length, it will be very easy for this O- to come into such a orientation so that it can attack this particular carbon. Whereas if I talk about a 5-membered ring, it will take time to come into that proper orientation so that it can attack this particular carbon center. So there's also one more principle involved, that you have to do this reaction for a very less amount of time. So if you do this reaction at low temperatures and a very less amount of time, your 3-membered ring, this product will be the major product. And if you do this reaction at high temperatures with taking a longer time, let's say 20 hours or 24 hours, then the major product in that particular case will be your 5-membered ring, right? So this is what I meant by a shorter span of time and a longer span of time. So this is where it matters, because this 5-membered ring will take a longer time to come into the proper orientation, or into, you know, in the proper orientation, right? In the proper orientation, so that it can attack this nucleophilic center. Whereas for this O-, it will be very easy to come into that orientation, because there's only a difference of 1 carbon between this oxygen and this carbon, whereas there's a difference of 1 2 3 carbons. So 3 carbons have to orient in such a way so that this O- comes into the right position to attack this carbon, whereas over here only 1 carbon has to orient in a particular way so that this O- can attack this carbon center. So a shorter span of time and at lower temperatures, your 3-membered ring will be more stable, whereas at higher temperatures and a longer span of time, if you do the reaction for a longer span of time, then the major product will be your 5-membered ring. So I hope this video was helpful to you. Do give this video a big thumbs up, and do subscribe to my channel. It's the red button below, and do not forget to subscribe to my channel if you want to watch my videos in Hindi, that is the chain reaction. I will put the link to that particular channel in the video down below, so you can just click it, subscribe it, and just wait for the videos to come to that channel soon, right? I will not be stopping this channel will continue as it has been, but for helping my fellow people who are not able to understand English or are facing difficulty in understanding this line in this particular language, I will help you out by, you know, making lectures in Hindi. So I mean, I really hope that you like this initiative, and thank you so much.